Hear my voice? You guys hear my voice? Okay, yes. So last time I wanted to finish lecture note 2, but because I spent too much time on probability and statistics in the first lecture, everything's a little bit delayed. So unfortunately, last time we couldn't finish the lecture note. So we need to finish the previous lecture note, and then we're going to start a new lecture note today. So if I remember correctly, we stopped somewhere around here, least squares assumption. I remember we finished how to compute OLS estimator in formula and also in an example. And now we need to discuss about the estimator's statistical property. So for example, we need to know at least the estimator is unbiased or whether it is consistent. If it is not unbiased or consistent, then what is the conditions under which we could have desirable estimators? So that sort of thing is the topic that we start talking about today. So without having any assumption, so far we made only one assumption, that is the conditional expectation function is linear in parameter. We have only linearity assumption. But in order to study the statistical property of the estimator, we have to make some additional assumptions. So I'm going to list some additional assumptions, and then we will discuss each assumption in detail one by one. I'm going to give you 3 assumptions, and we're going to call them as least squares assumptions. Actually, this approach is a little bit different from traditional approach. So first, we're going to cover these assumptions, and then I will let you know how this approach is different from the traditional approach in econometrics. So the first one is the conditional expectation of error term given the value of regressor is equal to 0. So when you have this conditional expectation form, then it may not be easy to understand what this means. But actually, the result of this assumption is easier to understand. Under this assumption, we can show that the covariance between error term and x, the regressor, is 0. So even if you have some information about the individual's characteristics, that observed information does not give you any additional information about the unobserved term. So if you have this additional assumption, as long as you have linearity and this additional assumption, conditional mean 0, then you can show that OLS estimators are unbiased. Actually, the proof for unbiasedness is pretty straightforward, but we are not going to cover the mathematical proof. But I want you to remember the first assumption guarantees that OLS estimator is unbiased. And then the second one is we have sample on regressor and the left-hand side variable. And this second assumption says that these x and y are identically and also independently distributed with some distribution. This assumption doesn't say anything about the underlying distribution, but this assumption is saying something about how we collect the data. So under the second assumption, we are sure that what we have, our data, is a random sample of size n. Actually, under this assumption, we can derive sampling distribution of the OLS estimators. Why do we need to have sampling distribution of OLS estimator? That's because we want to do statistical inference. We want to test some hypothesis, and we want to construct confidence interval. Without having sampling distribution, we cannot perform any statistical inference around our estimator. And the third one, we shouldn't have large outliers in both regressor and right-hand side, left-hand side variable. Mathematically, this assumption, the last assumption, is equivalent to saying that x and y have finite fourth moments, but we're going to go back to this point later in detail. Just a little bit more detail. The reason is because when we have outliers, then our OLS estimator becomes unreasonable. It doesn't make much sense. Okay, so let's look into detail about the first assumption. Error term is mean zero, conditional on our observation on regressor. So graphically, we can draw this population regression line, right? So although we don't know where this line is located, we don't know its slope or intercept, but we do know that under our assumption, we do know that there's a population regression line that is blue line over here. And at each point of x, so here as an example, we choose x being equal to 15 and 20 and 25. So at each point of x, we must have distribution of y, right? And this assumption says that the distribution has to be centered around the population mean. So conditional expectation of y, the left-hand side variable, has to be equal to the has to be on the straight line, the blue line. Then anything deviation, any deviation from this blue line can be regarded as error term. And as long as the situation is like this, then we can show that the error term has a mean zero at every point of x. So here, example. We want to regress test score on STR. STR is a student-teacher ratio, right? This is a very simplified version of the true equation. But let's start looking at this simple regression equation problem. So here, UI is error term. And the UI contains all the other factors that might affect test scores. Then our first question is, what are those other factors? We have to think about this very carefully in order to say whether this assumption is valid or not. So once we identify the list of other factors that might be included in the error term, then we will have to think about whether this assumption is still plausible. One way to do that is we have to think whether these other factors are correlated with x variable. If there is a correlation, if there is a non-zero correlation, then this assumption, this conditional mean zero assumption is not valid. So without having this assumption, we cannot have unbiased estimator. And also, it turns out that OLS estimator is not consistent. So the first assumption is very important. So think about other factors, possible other factors. One thing that I have right now is maybe for each school district. So here, observation, the unit for the observation is a school district in California. In Brisbane, we have many school districts like St. Lucia district and the Indooroopilly district, Chapel Hill, Kenmore. So in California, there must be lots of school districts like this. Student-teacher ratio is a determinant of test score. But that is not the only determinant of the test score. Maybe, how about family income, the average family income in the school district? Maybe some districts are more wealthier than other districts. Then kids living in wealthier district might have more resource. And therefore, they have more opportunity to learn. They could hire tutors and things like that. So parents' income might affect their kids' test score. And at the same time, because in that district, parents are rich, so they invest more money on their kids' school. So therefore, maybe in richer districts, school teacher ratio might be lower than other poor districts, right? Then family income is a determinant for test scores, and at the same time, it may be correlated with the school teacher ratio. Because there's a correlation, this assumption, conditional mean zero assumption, may be violated, right? Then if this story is true, then we cannot have unbiased OLS estimator. Then under what circumstances could we have this assumption satisfied? So one benchmark for thinking about this assumption is to think about ideal randomized control experiment. You can use a computer. If X is randomly assigned to people, so students are randomly assigned to different sizes of classes, and also patients randomly assigned to medical treatments, new medical treatments. Then, especially if this randomization is done by computer instead of people, if doctor is assigning their patients to different medication, then the doctor must consider the patients consider, right, intentionally or unintentionally. If there's no human, interference, then computer is doing this randomization. Then this information in X is randomly assigned, and therefore two different groups might have equal unobserved factors probabilistically. So in that case, we can say that this first assumption is satisfied. Conditional on X. There is no additional information about the error term. So error term, this X variable does not convey any additional information about the underlying unobserved factors. In that case, we have this assumption satisfied. So in natural science, scientists are doing lots of experiments. And in that kind of natural science, the experiments in natural science, they can do this kind of randomization because subjects are plants, cells, and animals, But in social science, subjects are human beings. So we cannot, in many cases, running randomized experiment can be unethical, so we cannot do this. Or even if it can be ethical, running a social experiment can be very expensive. So a completely ideal randomized experiment is really rare in social science. So whenever we run, whenever we analyze data using linear regression, we have to really think about this assumption, because without having this assumption, we're going to lose all the really good properties of OLS estimator, unbiasedness and consistency. And the second assumption is a little bit easier than the first one. As long as we sample individuals from same population independently, then we can claim that the second assumption is satisfied. X and Y are IID from some population. So one common case is if you have cross-sectional data, then mostly this assumption is regarded as satisfied. But another type of data set that is widely used in economics is time series data or panel data. If we observe the same individual over time, then the random variables that are attached to that the same person may be correlated over time. So in that case, we don't have this assumption. This assumption is violated. Therefore, we have to develop new econometric technology to handle this kind of serial or autocorrelation. Later, when we discuss about time series analysis, we will come back to this assumption and think about how to relax this assumption later. But as long as we are studying cross-sectional data, then this assumption is satisfied. The last one, the third one, we shouldn't have many large outliers. So technically, the technical statement for this third assumption is this: expectation of x to the 4 is finite, and expectation of y to the 4 is finite. But this technical term is not intuitive, so you should remember just as it is. We shouldn't have large outliers. Then what's the problem of large outliers? If you have large outliers, then basically OLS estimator is some extension of sample average. We know that sample average is sensitive to outliers. Therefore, our estimate can be very different from the underlying true population parameter that we want to know. So in many cases, large outliers may be because of typo or coding error. When people are collecting information, they could make some mistake. Like, they could add 2 more zeros. So when they are collecting some information about family income, reasonable range may be like, between, $40,000 to maybe if you're rich, $200,000, maybe $300,000. But, because, people are collecting data, so they might give additional 2 zeros at the end of their, or 3 zeros. Then, we could have really unreasonable number for family income, right? So sometimes we could detect that kind of obvious error. And whenever we have outliers, then we can delete, we can drop out that observation because that observation is meaningless. So here we have a graphical example. So the dot with a red circle. So when we regress, by the way, these black dots are all the data for some exercise. X is a regressor and Y is the dependent variable on the left-hand side. When we regress Y on X using all the data points, including this isolated dot, then we will have the OLS regression line that has positive slope, like that. If we do the same exercise, but without this dot with a red circle, then the OLS regression line is more flat, right? So therefore, when we are interested in estimating the slope parameter of this exercise, then our estimate for the slope parameter is going to be very different when we include outlier and when we delete the outlier. So in that case, we have to examine this observation more carefully. We have to look into this data set, and we have to determine whether there's a coding error or some mistake, things like that. So if you think that number, especially the value on y is more than 17,000. I don't know what application is this, but depending on the application, you could say that this kind of large number cannot happen in reality. If that is the case, then you drop this observation and run the OLS regression line. Okay? So it is important to plot your data just like this. And also, it is important to understand the institutional background. So for example, when you run the test score on student-teacher ratio, if you found a student-teacher ratio that is greater than 1 or below than 0, then obviously that is an outlier. So there must be coding error. So you have to drop that observation because the ratio has to be between 0 and 1, right? Okay, so we reviewed 3 least square assumptions. And now, under these assumptions, we want to discuss about sampling distribution of OLS estimator. Whenever you have a random variable, you will have a distribution for that random variable. So sometimes, instead of saying you have a random variable, you could say you have a distribution. This is the same thing. Whenever you have a random variable, you have a distribution for that random variable. So having a random variable is the same as having a distribution. You have to understand that estimator is a random variable because estimator is a function of random variables. You observe random sample, and using the random sample, you calculate the estimator. Therefore, estimator is constructed based on your data. If you have random data, then estimator is also random. If you understand estimator is a random variable, then you should know that the estimator has a distribution. More generally speaking, a function of random variable, random sample, has a distribution. The distribution of function of random sample is called sampling distribution. So estimator is a special case of a function of random sample, right? So the distribution of estimator is called sampling distribution of that estimator. Here we have OLS estimator. That is why we say we have sampling distribution of the OLS estimator. So sampling is attached to the distribution for a certain kind of random variable. In this case, that is OLS estimator. Again, sampling distribution is distribution for a function of random sample, right? So estimator is a function of random sample. Later, test statistic is also a function of random sample. So we will have sampling distribution of test statistic. Actually, sampling distribution of test statistic is derived from sampling distribution of OLS estimator. Once you know the sampling distribution of estimator, then it will be straightforward to derive sampling distribution of test statistic. So anyway, so once you understand the estimator is random, then you have to make a distinction between estimator and the realization of estimator. Random variable and realization of a random variable. So it's just, comparison is just like this. You have experiment to toss a coin. Before you toss a coin, you know that probability of having head is 1/2 and probability of having tail is 1/2, right? So you have a distribution. You have a random variable. But once you toss a coin, then you see the result of the experiment. If it is tail, then x variable has a value of 0. If it is 1, if it is head, then you will observe value of 1, right? So this 1 or 0, the outcome of the experiment is realization of the random variable. So most case, actually almost all the time, when you run the regression using computer, you are dealing with realization of samples, the random sample. But theoretically, you need to make a distinction between random sample and realization of random sample. In computer exercise, you will always have realization of random sample. But on paper, on your textbook, you need to make a distinction. So one easier way to think about the randomness of the estimator is this. Imagine this kind of hypothetical situation where you are collecting a random sample of size n, say 100, from a large population. You select 100 people and interview them to collect some information, say their income. And you collect the data, and then you estimate something. That is what you did today. And you repeat the same thing tomorrow. You're going to select 100 people, but maybe you're going to see different people, right? Because this is large population. So every day, you select 100 people from pool of population. Because you will have different people, their incomes are different, therefore your estimators are different, right? I mean, your realization of estimator is different every day, right? If you keep doing this infinitely many times, then you will have nice distribution of the estimator, right? So here, we are talking about distribution of OLS estimator. So we are collecting data on X and Y every day, but because we are interviewing different people, the values for X and Y are different. Therefore, our OLS estimator will have different numbers. Today, we have different number. Tomorrow, we have different number. We keep doing this many times. Then we will have distribution of OLS estimator, right? So each time, our value of OLS estimator is different. Therefore, OLS estimator has some uncertainty. And this uncertainty is summarized as the sampling distribution. We want to say something about the uncertainty because, after running the OLS estimator, we don't want to say just, our estimate is this number. This is what fortune teller might be doing. We are a scientist. After saying that our best guess about the population parameter is this number, we want to say something about uncertainty around our conjecture. So in order to do that, we need to have sampling distribution. Once you have sampling distribution, then we can test the hypothesis. Most commonly tested hypothesis is this. The number is equal to 0. Underlying parameter is equal to 0. And alternatively, we can consider the confidence interval for the slope parameter. Okay. So again, under the assumptions, 3 assumptions, we can show that OLS estimator is unbiased, which means that expectation of OLS estimator is the same as the true population parameter. Without having sampling distribution, expectation of OLS estimator doesn't mean anything. You have expectation only when you have a distribution. We can say the same thing for intercept parameter. OLS estimator for the intercept parameter is also unbiased. Also, we can derive variance of OLS estimator. We are not going to derive variance of OLS estimator mathematically, but I want to characterize, especially I want to give you two very important, I want to emphasize 2 important aspects of the variance. Just like sample mean, we had a variance of sample mean, right? When sample size increases, variance of sample mean decreases. We have the same aspect for OLS estimator. If we increase the sample size, if we have large sample, then the variance of an estimator is small. So if we consider these two things, expectation of estimator is centered around the true population parameter beta 1, and variance is decreasing when we increase the sample size. We can, say that OLS estimator is consistent. The OLS estimator is going to be very close to the true population parameter beta 1 when sample size goes to infinity, right? And also, if you have the mathematical formula for the variance of OLS estimator, then you can see that variance of x, the random variable x, is inversely proportional to the variance of OLS estimator, right? So if you have an option to choose two different data sets, then it is always a good idea to have a data set with larger variance of x variable. Then you will have more condensed, more precise estimator. This graph will give you some difference between these two different data sets. The left panel has low variation in x variable, but the right panel, we have high variation for x variable. If you have data like the left panel, then it's hard to know whether the population regression line is going to be positive, the slope is positive or negative. But if you have large variation in x, then as you see on the right panel, the slope is going to be more clear. So in that sense, our estimate for the OLS estimator is going to be more precise. Generally speaking, we cannot derive sampling distribution exactly. If you want to have exact sampling distribution, then you need to have additional assumptions. But fortunately, when sample size increases, we can develop asymptotic theory for the estimator, and then we can show that the ratio between the difference between our estimator and the true parameter value to the standard error of our estimator is approximately distributed as normal distribution, mean zero, and unit variance. Then using this approximate distribution, we can do hypothesis testing and we can construct confidence interval. So this exercise is very similar to what we did for sampling average to estimate population mean. So we're gonna study how to do hypothesis testing and confidence interval in the next lecture slide. Any questions so far? All right. View full screen. So outline of this chapter. By the way, today we are going to cover chapter 5 of the textbook. Chapter 1 to 3 are just a review and introduction, so we did it very quickly. And we spent some time on chapter 4, and now we're gonna go into detail about chapter 5. And chapter 4 and 5 will be included in your mid-semester exam. And I'm not sure about chapter 6. But it is certain that chapter 4 and 5 will be included in mid-semester exam. Okay, outline. We will talk about hypothesis testing concerning about the slope parameter and the confidence intervals. And we're going to discuss about regression when x variable is binary, when x variable takes only two possible values, 0 or 1. And we will talk about heteroskedasticity and homoskedasticity. And we will discuss about some properties of OLS estimator. And we will briefly discuss about student t distribution. So our objective is to learn about the slope parameter, slope population regression line, using the data. And like we discussed before, there's a sampling uncertainty. So we need to take into account this sampling uncertainty in our analysis, data analysis. So the textbook says that there are 5 steps towards this goal. The first one is we need to state clearly our population object of interest. In this case, we are interested in slope parameter. Beta 1 is the object of our interest. And then we will provide an estimator of this population object. In our context, we are going to compute OLS estimator for beta 1. So beta 1 hat is our estimator. And then we need to derive sampling distribution of the estimator. In large samples, we can use normal distribution by applying central limit theorem. And then we have to compute the standard error of the estimator, and then we need to conduct hypothesis testing and construct confidence interval. We need to construct t statistics. So this 1, 2, 3, 4, 5. These are 5 steps that we are going to do repeatedly many times. Okay, so in general form, the first line we have regression equation. Y on the left-hand side variable, and on the right-hand side variable we have very simple linear function, linear parameter. And the interpretation of beta 1 is this ratio, the ratio of left-hand side variable to, the increment of left-hand side variable to the increment of the right-hand side variable. In other words, when we change x variable, we are interested in what would be the change on the left-hand side variable. So we are interested in causal effect. When you change x, what this change causes on the left-hand side variable. So in other words, beta 1 measures causal effect, or sometimes it is called marginal effect. Causal effect is different from marginal effect, but in our context, especially when all the assumptions are satisfied, assumptions 1 and 2, 3 are satisfied, causal effect becomes identical to marginal effect. And in your homework assignment, you are asked to measure marginal effect. Right. So in this case, the marginal effect is beta 1. But if you have different problem, then marginal effect may be different from slope parameter. Right? So if you have more complicated function, like if you put log of y instead of just y, then derivative of y with respect to x is not going to be the slope parameter. You need to do some just a little bit of mathematics to derive marginal effect. Anyway, that is related to your homework. But in this simple case, slope parameter is equal to the marginal effect. Estimator, we're going to use OLS estimator and sampling distribution. In order to derive large sample distribution of OLS estimator, we're going to make the following assumptions. We already made these 3 assumptions: mean zero assumption, and IID assumption, and no outlier assumption. Then first thing, if you have sampling distribution, we can conduct hypothesis testing. So think about null hypothesis that under which we believe that beta 1, the true value of beta 1 is 0, which means there's no relationship between x and y. So general setup looks like this. Null hypothesis. We can test this null hypothesis using two-sided alternative. So under the null, we believe that beta 1 is equal to beta 1 superscript 0. Here superscript 0 can be 0 or some other number that is coming from economic theory. Alternative hypothesis. You must have some typo here. H1, subscript H1 is the notation for alternative hypothesis. We believe that the null is not right. That is two-sided hypothesis testing. And the beta 1 superscript 0 is the hypothesized value under the null hypothesis. We could think of one-sided alternative. So we have different alternative hypotheses. In this exercise, we're going to focus on two-sided alternative hypothesis because that is a lot more simple. So the way we conduct hypothesis testing is to construct this ratio, t statistic. Because once we have this statistic, then we know that approximately this is normal distribution with mean 0 and standard deviation 1. Right? This is approximate. This approximation holds only when sample size is large. But can you compute the left-hand side of variable? So can you compute beta 1 hat minus beta 1 divided by standard deviation of beta 1 hat? I'm asking you a question. So can we compute this last one? Can we? Do we know beta 1? No, we don't know beta 1, right? So we cannot calculate this ratio, beta 1 hat minus beta 1 divided by standard error. We cannot compute this. We can do this only when we have some number for beta 1. So here we have null hypothesis. Under the null hypothesis, we believe that beta 1 is a beta 1 superscript. And if we plug beta 1 superscript over here, then finally we can compute this ratio. And if null hypothesis is correct, then that ratio is normally distributed. In general, the tested statistic has this form: estimator minus hypothesized value, the value under the null hypothesis, divided by standard error of the estimator. Previously, when we estimate the population mean, this is the tested statistic that we used. And now, for OLS estimator, this last expression is the tested statistic for OLS estimator. So the formula for T ratio is very simple. And also this is quite general across many different estimators. Standard error is a consistent estimate of the standard deviation of the estimator. And we discussed about standard deviation in the previous lecture, but we didn't derive it. We just discussed about the variance of the OLS estimator. When sample size increases, we're going to have smaller variance, which means our estimate is more precise. And when variation of x, the regressor, is large, we will have smaller variance of the OLS estimator. But turns out that this variance, the true variance, depends on some unknown parameter. Therefore, we have to estimate this variance. And luckily, many econometric softwares, such as Stata and eViews, report standard errors by default. if you're interested, you should study the formula for standard errors, but we don't do that in this course. But we're going to use the theta outcome to construct confidence interval or hypothesis testing. So we're going to use just the standard error that is coming from standard deviation. That is coming from theta. Okay. All right. Then T ratio is copied and pasted over here in the first line. And then the next step is we need to choose the level of significance. Typically, we choose 5%. If you want to be more conservative, you can choose smaller number, 1%, even 0.1%. That reflects how conservative you are in terms of when you are interpreting the sample information. But many people are using just 5% of significance level. So we will follow the convention of using 5%. And then based on this, our choice of significance level, we can make a decision whether to reject the null hypothesis or not. So we have decision rule here. The ratio is greater than 1.96 in absolute value, then we reject the null hypothesis. If the ratio is less than 1.96, do we accept the null hypothesis? Do we accept the null hypothesis? No. Yeah, right. We do not accept null hypothesis. Right? Only thing that we can say is we don't have sufficient statistical evidence to reject the null hypothesis. That is our correct statement. But many applied people often say that we accept the null hypothesis. But this is not theoretically correct. Alternatively, we can reject the null hypothesis if p-value is smaller than our choice of the level. Third option is we construct 95% confidence interval and see whether the hypothesized value is inside or outside the confidence interval. If it is outside the confidence interval, then we reject the null hypothesis. Okay, so 1, 2, 3 are equivalent way to conduct a hypothesis testing. Here, let me ask you a question. What is significance level? Yeah, 5%. But yeah. We choose 5% here. What is meaning of significance level? That is a probability of something. Yes, right. Type 1 error probability. So type 1 error probability is something that we choose. By the way, what is type 1 error? Yeah, we reject the null hypothesis, but the null is true, right? So that is our mistake. We are making a mistake that reject the null hypothesis when it is true. So alpha is level of, alpha is a probability that we can make that sort of mistake. This procedure relies on the large N approximation. If sample size is large, then we know that the T ratio is standard normal distribution. Typically, when sample size is greater than 50, then we can say we have large enough sample. And we can perform this large sample hypothesis testing. But the more, the better. And in economics, most sample size is way, way larger than 50. So we can use approximate, the normal approximation for the standard, for hypothesis testing and confidence interval. If you are more conservative, say you choose 1% of significance level, then the decision rule is exactly the same as before, but instead of 1.96, you have to use 2.976 or just 2.76. 2.576 or 2.58 approximately. All right. So here, this is a computer outcome. We regress test score on student-teacher ratio, and we have estimate for the coefficient in the first column, as you see over here, and the red numbers are standard error. And right below the table, we have equation with numbers, right? Test score is equal to 698.9 minus blah, blah, blah. And right after the estimated regression line, we give some measure for goodness of fit, like R square and SER. And right below our estimate, we write standard error in parentheses. So this is a standard way to report our estimation results. And here, T ratio can be computed in this way for the slope parameter. So negative 2.28 minus, we are interested in testing the null hypothesis under which we believe that beta 1 is 0. So we just subtract 0 and divided by standard error, which is 4.38 greater than 1.96. Therefore, we reject the null hypothesis. We reject the null hypothesis, which means we have sufficient statistical evidence that by which we reject the belief that beta 1 is 0. Similarly, we can use p-value, or we can use 95% confidence interval to do hypothesis testing. All right, so let me stop here, and let's have a 10-minute break. Let's have a break until 11 o'clock, and then we will start from here. So please come back by 11 o'clock. Yes.
So in the third
Okay. Okay, so here the first column, the the name for the first column is coefficient, but it doesn't mean that these numbers are the true parameter value. The first column, these numbers are our estimate for the coefficient, not the true coefficient. But here, these red numbers are coming down to here in parentheses. So this expression is a standard way to write down our estimation results. Regression equation, estimated regression equation, under which we put down standard errors in parentheses, and next to it, we write down R-square or SER. And we just reviewed 3 ways to do hypothesis testing. And in this testing exercise, we assume that beta 1, the slope, is equal to 0 under the null hypothesis. So therefore, this number is plugged into the formula for t-ratio. When you compute this, you will have 4.38. That is greater than our critical value when significance level is 5%. So we reject the null hypothesis. P-values are listed over here for each parameter value. And for this p-value, and also here the t-ratio, so this negative 4.38 is computed just like this. So the third column and the fourth column, these columns are t-ratio and the p-value that are associated with this particular null hypothesis. The null hypothesis, we believe that the parameter value is equal to 0. So this is default null hypothesis for this table. And if you have different number under the null hypothesis, then how would you do the hypothesis testing? So suppose instead of 0, you have 1. Oh, so negative 1, say negative 1. Suppose you have negative 1. Then using this table, can you do a hypothesis testing? You have 3 options. First option, you can use t-value. But for these t-values, default null hypothesis is this one. But your null hypothesis is now different. That is negative 1. Under the null hypothesis, you believe beta 1 is negative 1. So you cannot use t-ratio. How about p-value? For p-value, underlying null hypothesis is this. The default null hypothesis is this. You cannot use this p-value. But here we have confidence interval. Under our new null hypothesis, we believe beta 1 is negative 1. Beta 1 is between, so we need to see whether beta 1 is included in this confidence interval. Is it included in confidence interval? No, yeah. Negative 1 is greater than upper bound of this confidence interval. So do we reject the null hypothesis? Yes? Yes. So yeah, right. So decision rule. A little bit confused. Reject the null hypothesis when the hypothesized value is outside the confidence interval, right? So negative 1 is outside the confidence interval, so we reject the null hypothesis. Yes, great. So far, the significance level is 5%. What if we have 1%? So we use the same null hypothesis. Beta 1 is 0 under our null hypothesis. But now we change our significance level from 5% to 1%. The first method, t ratio. This number has to be compared against different number. So 1.96 is not valid anymore. This one is associated with 5% of significance level. If you remember the significance, the critical value for 1% hypothesis testing, then you can use the first method. That is 2.5 something. So this number, 1.65, I'm talking about 1% significance level. Yeah, 1%. So look at this. If you're using 1% significance level, then the critical value is 2.58. So instead of 1.96, you have to use this number. So here, 2.58 is smaller than our t ratio. So we reject the null hypothesis even when you are more conservative. We can have the same result even when we are using p-value. P-value is very small. Essentially, it is 0. So it is obviously smaller than 1%. So we reject the null hypothesis. However, we cannot use the third method. 95 confidence interval is not linked to 1% of significance level. It is linked to 5% of significance level. So if you want to construct confidence interval for 1% of significance level, you need to construct 99% confidence interval, which is going to be different from this number. And you should know how to do that. So let me ask you a question. I'm not going to ask you to compute 99% confidence interval. Instead of doing that, do you think 99% confidence interval is wider than 95 confidence interval or narrower? Yeah, it should be wider. Should be wider? Okay, so think about this formula. Confidence interval is centered around our estimate, and 1.96 times standard error. Standard error is independent of alpha. For different alpha, we're going to choose different number for this place. When alpha is 5%, we're going to use 1.96. When alpha is 1%, we're going to use a larger number, 2.58. Now, let me ask you a question. 99% confidence interval, is it wider or narrower? Yeah, it should be wider, right? Yeah, great. P-value can be used for hypothesis testing, and also confidence interval. So here, let me explain repeated sampling just once again because it appears again. So actually, I already explained this repeated sampling. Today, we interviewed 100 different people and collect information and run regression, and we obtain estimator. That is today's realized value of the estimator. Tomorrow, we repeat the same exercise using different sample, randomly selected different sample. Then tomorrow, the realization of an estimator is different. Standard error will be different. Every day, we will have different estimator and different standard error, which means every day, we will have different confidence interval, right? Now, another way to interpret the confidence interval is if we keep doing this, then every day, infinitely many days, we will have infinitely many different confidence intervals. 95% confidence interval. What does that mean? 95% of time, this confidence interval, actually now the confidence interval is random. The confidence interval will contain the true parameter value. So if we repeat this 100 days, then on average, 95 days, our confidence interval will include the true parameter value. If we repeat this 10,000 times, then we will have 10,000 different confidence intervals. The confidence interval will be different. This interval itself is random. Then, if we have constructed 95% confidence interval, then 10,000 times. What is 9,500 times? The confidence interval will include the true parameter value. So that is another way to interpret the confidence interval. Previously, I gave you only one interpretation of confidence interval. Confidence interval is a set of parameters that cannot be rejected by 5% two-sided hypothesis testing. So here we have one additional interpretation for the same confidence interval. Now, sometimes X variable is binary, which means we have either 0 or 1 for the regressor, X variable. Binary variable is very useful because it can express some qualitative information, whether you are female or male, whether you are a student or not, whether you graduated from high school or not, whether you are going to a class with a small class size or large class size, things like that. So suppose, let's define this random variable. X is equal to 1 if the school district has small class size. Otherwise, it is 0. X is equal to 1 if the observation is female. Otherwise, it is 0. X is equal to 1 whether the subject of the experiment is treated by new drug, or otherwise it is 0. So this binary regressor is very useful for this kind of qualitative information. What is quantitative information? When you have X variable that is quantitative information, then the magnitude of the number is important. Instead of the, so small class size. So instead of this binary regressor, you could have exact number for the student-teacher ratio, right? Then the ratio becomes quantitative information. 0.2 is smaller than 0.3. 0.3 is smaller than 0.7, right? So when magnitude is important, then we say we have quantitative information. But we have different classifications. And we have qualitative information, then we are going to use binary random variable like this. In econometrics, we often use this term, dummy variable. When we have 0, 1 binary random variable on the right-hand side, X variable, then we say that we have dummy variables on the right-hand side. If we have dummy variable, then beta 1 is not a slope anymore. The interpretation of slope doesn't make sense because on the real line, only 2 points are relevant, and the slope is relevant when you have continuous variable. But X can take only 2 different numbers. Then slope doesn't make sense. The interpretation of slope doesn't make sense. Then how can we interpret this parameter beta 1? That is our question. So copy and paste our regression equation once again here, but only difference is X is now either 0 or 1. When we have linear regression line, basically, the regression line represents conditional expectation of y given x. And we make this assumption. This conditional expectation is beta naught plus beta 1 times x, right? Now we start our discussion from this definition. x takes 0 or 1. So let's consider the case where x is equal to 0. If x is 0, then y becomes, so here this x is 0, then second term disappears. So y is beta 0 plus error term. Then conditional expectation of y, the expectation of y for the group with x being equal to 0, that is just beta naught. So interpretation for the intercept is this. The average, the population mean for the group of people with x is equal to 0. Now x is equal to 1. Then if you plug 1 over here, then y is beta 0 plus beta 1 plus error term. So the group of people with x being equal to 1, average of y is beta naught plus beta 1. Then how do we interpret beta 1? That is difference between these two population means, right? Population difference in group means. That is beta 1. This is how we interpret the slope parameter beta 1 when x is a binary random variable. So let me give you an example. Go back to test score and student-teacher ratio, and we suppose we observe dummy variable. Now, instead of using x, let's use different notation, d, because when x is binary, the variable is called dummy. So many people are using d for dummy variable. D is equal to 1 when the school district has less than, so the student-teacher ratio is less than 20%. For student-teacher ratio greater than 20%, the dummy takes a value of 0. Using data and using the data, we run the regression. And these numbers are coming from the computer. Now, we are going to compare this regression results with our previous exercise. We had two different groups, right? And the group was divided exactly in this way. So we had small class size and large class size. For each group, we computed sample average over here, and we also computed standard deviation. This is the sample size for each group. So when we take difference between these two, difference between these two average scores, it has to be 7.5, right? So when we take this difference, the result is equal to our OLS estimate for the slope parameter. So our interpretation is correct. Actually, no, our interpretation has to be correct even before looking at this example. This example is coincided with our interpretation. And the standard error, the formula for the standard error looks like this. And using these numbers over here and the sample size, we can compute the standard error, and the number is 1.8, which is identical to standard error that we got from regression exercise. So this is how we interpret this regression. So summary, beta naught is mean, population mean of variable y for the subpopulation with x being equal to 0. Beta naught plus beta 1 is mean of y for the subpopulation with x being equal to 1. So beta 1 is just difference between these two groups. And we can construct t-statistics and confidence intervals in the usual sense. We don't change our formula for t-statistic or confidence interval only because we have binary random variable. The way we are doing statistical inference is still the same. So when we have binary regressor, this is another way, and actually simpler way to do difference in means analysis. We're going to use we're going to use a dummy variable for more complicated exercise in the future. Now, let's discuss about heteroskedasticity and homoskedasticity. What is heteroskedasticity and homoskedasticity? You know, it's not even easy to pronounce these two things, heteroskedasticity and homoskedasticity. And actually, so far, we allow the heteroskedasticity. So homoskedasticity is a new concept in this discussion. So we are going to discuss about what is the consequences of assuming homoskedasticity and the implication of computing standard errors, right? So we're going to discuss about something like this. So let me define the term homoskedasticity. We say error term is homoskedastic if conditional variance of error is constant, which means the variance of u is not a function of x. No matter what the value of x, the error term has the same variance, homoskedasticity. If we allow this variance to be a function of x, that is more general, then we say the error is a heteroskedastic, or we have a heteroskedasticity assumption for the error term. You know, you need to do some exercise. You know, you need to do some practice to pronounce these two things. I did it a lot. So in the previous example, implicitly we assume that two different groups have two different variants. So the way to estimate the standard error looks like this. So here in this formula, we have standard deviation for small group and standard deviation for large group. So this formula reflects the fact that we are allowing two different groups to have two different variants. If we assume that two different groups have the same standard deviation or same variance, then the formula becomes like this. Standard deviation for S is the same as standard deviation for L, large. Then we can pull this thing out of the square root, right? So the formula becomes like this. And SP is a pooled estimator of the standard deviation. So equal group variance, that is the same thing as homoskedasticity. Here, homo means equal. Maybe it comes from Greek language, Latin, I don't know. It doesn't matter, actually. And the unequal group variance, that is a heteroskedasticity. So here we have the same graph of test score and student-teacher ratio. And here population regression line over here. And at each different point, we have a distribution of y, right? Distribution of y. For small, so if this shape of the distributions are correct, then for small student-teacher ratio, the variation is small. And for larger student-teacher ratio, the variation of test score becomes large. So variance at x is equal to 25 is bigger than x is equal to 15. So this graph represents that the error term is a heteroskedastic. Right? So this is something that I already explained. So yeah, so variance of error term is a function of x that depends on x. Then in that case, we say error term is a heteroskedastic. once you calculate the regression equation, then you can compute the estimated regression equation line, and also you can compute fitted value. So say you have fitted value like this. So yeah, these dots are the data point for different exercise. So here, X is years of education, and the horizontal line measures average hourly earnings. So for group of people with smaller number of years of education, the variance of wage income seems to be small. But for those people who studied more, the variance of wage expected income seems to be large, right? So in this example, it's quite easy to say that error term is a heteroscedastic instead of homoscedastic. So if you have this kind of data, it's quite clear to say that homoscedasticity assumption is not going to be valid. We need to allow heteroscedastic error. This is the data scatter diagram for test score example. Is this a heteroscedastic or homoscedastic? Not clear, right? So looks like in the middle you have larger variation than this, boundary point. But at the boundary you have smaller sample size, so it's hard to know, right? But anyway, so for some exercise, for some applications, it is easier to see whether the errors are homoscedastic or heteroscedastic, but not always. For this kind of application, it may not be easy to say whether the errors are heteroscedastic or not. So actually, when we calculate the standard error using the data on student-teacher ratio, we allow the heteroscedastic errors. So then now what we are going to do is we're going to discuss about the implications of a homoscedasticity assumption. So in order to do that, let's review the three least square assumptions. The first one is mean zero assumption for the error term, the conditional mean zero. And the second one is IID assumption. And the third one is there's no outliers. And now homoscedasticity concerned about the variance of the error term as a function of x. If this depends on x, then errors are heteroscedastic. If this doesn't depend on x, if this variance is a constant, then we say error is a homoscedasticity, right? But these three assumptions, they don't say anything about this variance. However, this homoscedasticity assumption has been quite important in statistics and econometrics historically. The reason is because if we assume, so in addition to these three assumptions, if we assume errors are homoscedastic, then we can derive some additional properties for the OLS estimator. The first one is called the Gauss-Markov theorem that says that in addition to these three assumptions, if we assume homoscedasticity, then OLS estimator has the lowest variance in the class of estimators that are linear in left-hand side variable y. This is quite nice result. So we're going to discuss about this Gauss-Markov theorem once again later. And then another implication of homoscedasticity assumption is our estimator is going to be the same, but our formula for standard error is going to be much simpler. So derivation of the variance of OLS estimator is simpler. So when we have this simple formula for standard error, then we say that standard error is a homoscedasticity only standard error, right? In order to make a distinction, the standard error that we obtained so far, until now we allow the heteroscedastic error. So the standard errors that we have obtained so far are called heteroscedasticity robust standard errors or just robust standard errors. If it is too hard to pronounce this thing, then it is totally fine just to say your standard error is a robust standard errors. So historically, people assume the homoscedastic error, and then they show all the good properties of OLS estimator. OLS estimator is precise, and the standard error, derivation of standard error is so nice and simple. However, the problem is the formula for standard error is correct only when errors are really homoscedastic. And when you are analyzing economic data, the real problem is homoscedasticity assumption doesn't hold for most data. Most economic data, homoscedasticity assumption is not valid. Then when you have economic data for which homoscedasticity assumption is not valid, if you assume homoscedasticity mistakenly, then your standard error is going to be wrong, right? If you have wrong standard error, then your hypothesis testing is going to be wrong and your confidence interval is wrong, right? So when you have heteroscedasticity, when you have data for which heteroscedasticity is likely, then you should not assume homoscedasticity. Even if your data is fine for homoscedasticity assumption, it is still okay to use heteroscedasticity robust standard errors. Because when there's no homoscedasticity assumption, then robust standard errors is going to be equivalent to standard error for homoscedastic error only, right? So in any case, you should use heteroscedasticity robust standard error. It has to be default for your data analysis. You have to use robust standard errors instead of assuming homoscedasticity. Okay? So, so far we didn't discuss about this, but the first line, regress, is the command for doing the following. We're going to regress test score on student-teacher ratio. After comma, we put this option, robust. When you put this option, then Stata will compute robust standard error. Without this, Stata will compute homoscedasticity only standard error, which may give you invalid p-value, invalid confidence interval, and which will lead invalid statistical inference, right? So you have to put comma and robust option in Stata. Always. This has to be the default. Okay, so now we discussed about homoscedasticity assumption, implication of that. So now we're gonna discuss some additional theoretical foundations of OLS estimator. We already studied quite a lot about OLS estimator, right? So first of all, we learned that OLS estimator is unbiased and consistent. And we have a formula for heteroscedasticity, robustness, and the errors. And we can construct confidence intervals and test the statistics. And in reality, so many people are using OLS estimator, and they all understand what's going on when you are presenting your research outcome using OLS estimator. So, so this is kind of a common language in econometrics and statistics. So it's quite good. But is this really a good reason to use OLS? There might be a better estimator than OLS. Yes, there are many other good, better estimator, more efficient estimator. And also, you might wonder the second question: what happened to student T distribution? We never used in this class. We never used the student T distribution. Maybe in your earlier course, like statistics, or if you already learned econometrics before you're coming to UQ, then probably you have used the student T distribution, right? What happened to this distribution? So let's discuss about this kind of things. So in order to do that, we need to add a few more assumptions. So first three, these are the three assumptions that we already made, least square assumptions. And now, fourth one is error is homoscedastic. And fifth one is error is normally distributed. 4 and 5 are additional assumptions to least square assumptions. And for the rest of this course, we are not going to make these additional assumptions, 4 and 5. We're gonna study these additional assumptions only for now. Okay? Which one is better, having many assumptions or less assumptions? Many assumptions? Yeah. For the if you can have the same conclusion, the number of assumptions should be smaller. So maybe you can derive some complicated theoretical results under a set of assumptions. And then the next thing that you should try to do is you should try to relax these assumptions one by one, right? If you have more assumption, then that means your statistical analysis is not robust, because that depends on your assumption. So having smaller number of assumption is always more desirable. So anyway, for now, we included this fourth and fifth assumption. When we made the first 4 assumptions, we will have Gauss-Markov theorem. Assumptions 1 to 4, we can show that beta 1 hat, has the smallest variance among all linear estimators. So estimator is a linear function of sample on the left-hand side variable, y1 to yn. So we have certain class of estimators, and then within this class, we can say that OLS is using the sample information in the most efficient way. So its estimator, the estimator is precise, the smallest variance. So that is the result. And if you include the fifth assumption, error is normally distributed, then you can derive this additional, very nice result, optimality of OLS, as long as you have consistent estimator. So now your class of estimator is larger than before. You have class of consistent estimator. Within this class, OLS estimator has the smallest variance. So this class includes linear estimators or nonlinear estimators. So this one is a lot bigger class. But the problem is Gauss-Markov theorem really isn't that compelling because homoscedasticity assumption is not plausible for many economic data. Actually, almost all economic data, homoscedasticity assumption is unreasonable. And also, this result holds only for linear estimators. The class of linear estimator is very small compared to the all feasible estimators. And the optimality result is even less compelling because in addition to homoscedasticity assumption, we have to make normality assumption. So if homoscedasticity is not plausible in real data analysis, then this stronger assumption is even more unlikely, right? So this nice result of our OLS estimator, optimality. This is a theoretical result, but in real data analysis, it's not really relevant to our exercise, right? And also another drawback of OLS estimator is when you have outliers or some extremely large number observation or extremely small assumptions, small values on X, then OLS estimator is very sensitive to the outliers. So if you don't want to have such a sensitive estimator, then instead of OLS estimator, you could try different kind of estimator. OLS estimator is a generalization of sample mean, right? There is a estimator that generalizes sample median or sample mode, something like that. So that you can find many different classes of estimator. However, we're gonna still use OLS estimator in spite of some negative aspects of the estimator, because one of the reasons is still, many applied people are using OLS estimator for their research problems. And one of the objectives of this course is after this semester is over, we want you to be able to write an applied research paper, applied empirical research paper. For that purpose, OLS is perfect, right? So, many of you don't have much, experience of statistical analysis, right? So here we start from a baby step. Then, OLS estimator has to be the first topic that you learn for data analysis. Only after you feel comfortable about OLS estimators or some extensions of OLS estimator, you can learn more advanced estimators, right? So this is a natural step. Now, what happened to student t distribution? So under those 5 least square assumptions, especially the normality assumption, we can show that OLS estimators are also normally distributed for all n. So this is amazing. No matter what your sample size is, OLS estimator is normally distributed. So we have exact distribution for the estimator. The sampling distribution is exactly normal. And then when we divide the estimator by standard error, then the t ratio is exactly distributed as student t distribution with degree of freedom n-2. Why do we need to subtract this number 2? We need to subtract the number of parameters from the sample size. So in this simple linear regression problem, we have only 2 parameters. So the degree of freedom for this problem is n-2. But later, when we have more terms, so if you have beta naught, beta 1, and beta 2, then we need to subtract 3 from the sample size. That is the degree of freedom. When sample size is smaller than 30, then the t critical values, the critical values that you obtain from the student t distribution are quite different from the normal distribution, the critical value that you can obtain from the standard normal distribution. So here are the table. So when degree of freedom is 10, the 5% critical value is 2.23. It decreases like this as you increase the degree of freedom or as you increase the sample size, right? But when you increase the sample size to infinity, then it becomes 1.96. You are familiar with this number. What does that mean? Student t distribution converges to standard normal distribution. So when sample size is large, there's no difference between student t distribution and normal distribution. So when should you use student t distribution? If sample size is smaller than 50 and you really believe that error is homoscedastic and also normally distributed, then you can use student t distribution instead of normal distribution. But again, these two assumptions, homoscedasticity and normality assumption, these two assumptions are unlikely in real world. So we don't want to do this. And in most econometric applications, there's no reason to believe that U is homoscedastic and normal. And actually, there are many good reasons to believe that neither assumption is true. Luckily, in modern applications, most economic data have larger size than this, way, way larger size than this. Like, 10,000 sample size is quite common. And therefore, we can use just, approximate asymptotic theory to do hypothesis testing and construct confidence interval. So we don't have to make this homoscedasticity assumption and the normality assumption for data analysis in economics. We shouldn't do that, actually. We should not do that. Now, let's come back to our initial policy Suppose new teachers are hired so that the student-teacher ratio falls by 1 student per class. What is the effect of policy intervention on test score? Have you answered to this question? Right? So until now, we used only one variable to explain the test score, that is student-teacher ratio. Relevant question might be this. We had 3 assumptions for least square estimator. Do you think in this exercise, these 3 assumptions are reasonable? Right? If these assumptions are not reasonable, then we cannot answer to this policy question. So I think I already mentioned about this. So what could be included in U, this error term? So suppose family incomes are included in the error term. So for different school districts, there must be average level of family income. Some districts are richer, some districts are poorer, right? If rich district can provide more resource for the students, their kids, and at the same time, the districts have more resource for the school, then it is likely that family income is highly correlated with the student-teacher ratio, right? Rich people can invest more money on their kids' school, so they can hire more teachers. Then family income is positively correlated. Maybe this should be negatively correlated. Yeah, positively correlated. As long as this correlation is not 0, then the first assumption is violated. So if you believe this assumption is not true, then your OLS estimator is not consistent. And we cannot use the OLS estimator for answering this kind of important question, right? So as long as there's omitted factors that are correlated with our regressor in the regression equation, then we need to do something to fix the problem, right? So that is going to be what we want to do in the next lecture. All right. So I am very happy to finish this lecture note. And I wish you have a great time in this afternoon. Yeah, right. You guys have, kind of morning tea. You guys are invited to morning tea today, right? Maybe I'm confused. I'm sorry if I'm wrong. Anyway, have a great time until next week, and I will see you next time. I have consultation hours from 12:30 to 2:30. So if you have any question, please stop by.
So how is the more practice? Where is it? Do you have more practice for us?
So during the tutorials, you are going to do more practice, and also
From the starting?
yeah, using the data. And sometimes you need to derive something. But